One of the most common ways to generate light nowadays is by using a light-emitting diode or LED. Like the rest of the diodes, as we saw in a previous video, one of its characteristics is that it only allows the passage of electric current in one direction. But we didn't talk about why they emit light, so in this video we will see how an LED works. LED lights have several features that make them one of the preferred options to illuminate, such as having low energy consumption, greater impact resistance, and a longer lifespan, and because of this they are available in many different formats. But instead of going directly to analyze an LED, we will start reviewing how a common diode works, because in theory these can also emit light. It's just that they do it in an inefficient way. If we have a circuit with a lamp and a power source, energy will pass freely. This is because electrons can move freely between metal atoms and, when connected to the power source, they are forced to move. By adding a diode to the circuit, and depending on its position, the current can pass freely or be stopped. And the reason why this happens is because of its composition. Inside the diode, there is a semiconductor material such as silicon. More specifically, two types of this material. If we took a piece of pure silicon and saw its atomic structure, we will find that each atom has 4 valence electrons, which are shared with the other 4 silicon atoms around it, forming a crystalline structure with covalent bond. That is, they share their electrons, so there are a total of 8 valence electrons per atom. Resembling noble gases, the most stable elements known to humankind. If you don't like chemistry, don't panic. The important thing here is to understand that 8 electrons per atom is the magical number that keeps everything tightly connected. In fact, they are so connected that when a new electron wants to go through silicon, the electrons that make it up cannot move, hindering the flow of current. However, this can be changed through a process known as doping, in which impurities are added to silicon to control its conductivity and convert it into a N-type or P-type semiconductor. If we add impurities that have 5 valence electrons instead of 4, then we will have atoms with a total of 9 electrons. And since 8 was our magic number, we could say that one of the electrons will be left over or be freer than others, which will allow it, when connected to a power source, to move and act as a conductor. This alloy is known as N-type semiconductor because it has excess electrons, which, let's remember, have a negative charge. On the other hand, if we do the doping with impurities that have 3 valence electrons, we will have atoms with a total of 7 electrons. This means that we would have a gap, allowing electrons to move through it and generating a movement of the gaps in the opposite direction. Since this alloy would have 1 less electron than its stable form, it would have a positive charge, and it would be called a P-type semiconductor. Moreover, to simplify the visualization, we will say that each hole corresponds to a positive charge. This way, when a p-n junction is generated, depending on the polarization of the voltage source, there will be 2 possible results. If the positive pole is connected to the N-type semiconductor, and the negative pole is connected to the P-type semiconductor, the holes and free electrons will move away, preventing an electric current from being generated. This case is known as reverse polarization. On the other hand, if we reverse the polarity of the voltage source, the free electrons of the N-type semiconductor will be able to jump through the P-type semiconductor and close the circuit, allowing the passage of the current. This case is known as direct polarization, and it is precisely here that the physical phenomenon that produces the emission of light occurs. If we return to our visualization of the atomic structure, and we focus exactly on the point in which the 2 semiconductors make contact, we are going to find that electrons are being moved from an atom with more valence electrons to an atom with fewer valence electrons. This is extremely important, because this difference in the amount of valence electrons is also related to the amount of energy that they possess. In other words, an electron that is in an atom with 5 valence electrons has more energy than another electron in an atom with 3 valence electrons. This means that, every time an electron crosses this junction, there is energy that is being lost. But, as the law of conservation of energy says, energy cannot be created nor destroyed, it can only be transformed. And in this case, the energy that the electrons lost when jumping from one atom to another became light, or more specifically, photons. The fact that this happens at the atomic level has another implication. Since electrons move always from an atom A to an atom B, the amount of energy transformed in each jump will be constant, which in practical terms means that the emitted light will always have the same wavelength spectrum. This also implies that, by changing atoms A and B, that is, the impurities within semiconductors, we can emit lights with different spectra. Referring specifically to the visible spectrum, we can emit different light colors. At this point, we already know how the light is emitted, but we still don't talk about why, if this phenomenon occurs in a common semiconductor diode, we don't see them shine continuously. There are two main reasons. The first one is that in many cases our eyes are unable to see the spectrum that is being emitted. I couldn't find an exact demonstration of this, but I did find a video in which a solar panel emits infrared light when applying a voltage, and a diode generates a voltage by being enlightened, all of which is related to the same phenomenon. The second reason why a common diode does not shine is simply the shape. If we think the light is being generated only at the points where the two semiconductors are in contact, how are we going to see them if for the most part this area is being covered? In this pattern in which they describe one of the first light-emitting diodes, the solution is extremely simple: to move the semiconductors away from the connectors so that they do not cover the emitted light and reduce the thickness of one of them to such an extreme that light is able to pass through. In a way, we could say that this hasn't changed much to this day. Let's analyze an LED from the inside out. The first thing we will need is a substrate where we will put the rest of the materials. To this, we add a layer of N-type semiconductor, and then another thinner P-type semiconductor layer. The order is important because the transformation of energy occurs when reaching the latter layer. Then we add some cables so that the electric current can flow between the semiconductors and the light is emitted, being extremely thin so it doesn't cover it. Technically, only with this we already have a functional LED. But to be more efficient, we will add a small reflector to direct the light, which will be integrated in one of the electrodes. And before covering everything in a transparent epoxy resin so that the set is more resistant, we will add one last element, a layer of phosphorus, although this is used only in some cases such as white light. In this particular case, the diode is actually emitting a blue light, which upon impact on the phosphorus layer, causes this to emit a more yellow light. The mixture of these two spectra is what generates the perception of seeing a white light. The last thing I want to talk about is RGB diodes that can produce multiple colors. Although the truth is there is not much mystery left to it. The RGB name refers to the colors that compose it: red, green and blue. Well, indeed, within this type of LEDs there are 3 pairs of semiconductors specifically selected to produce each color, and by independently varying the voltage that passes through each of them, the perception of different colors is generated. I remind you that there are several more animations on my channel in case you want to check them out, and also that you can support me in Patreon to make more videos. That is all for now, and see you in the next episode.